time fully online because we have the pleasure to have a Spanish speaker who is 6 hours behind. So thank you very much, Fulvio, for accepting this invitation. Fulvio is a tenure researcher at the Institute of Environmental Assessment and Water Research from the Spanish Research Council. His research focuses on urban air quality and road transport emissions, with the main goal of understanding the sources of atmospheric pollutants, with particular attention to non-exhaust emissions from road traffic, their impacts and possible mitigations. From his European perspective, Fulvio is going to tell us about the state of the art in non-exhaust emissions from road traffic. So as usual, you can post your question in the chat so we can discuss later after the presentation. And I'll give the floor to Fulvio. Thank you.
Thank you, Maria Teresa. Actually, it's an honor for me to participate to this seminar. So thank you very much for the invitation to Greg and to the whole department. I prepared about 1 hour presentation, but I know that there is less time, so I will try to skip the ones which are not very crucial. The non-exhaust emissions from road transport is the topic of today. Even the definition of non-exhaust is actually not very clear, because depends on the study or on the report you can read different definitions. For example, for European emission reporting, you can see that the general separation is done between exhaust and wear emission. So where wear, it means brake and tire and road wear. So there's no mention here about the resuspension, which is actually one of probably the largest source of PM from non-exhaust processes. But the scientific knowledge on dust resuspension is less robust, probably. That's why in many studies you won't find a clear indication of road dust resuspension emission. But let's go on with this slide. This slide shows the trend of official emission reporting in the 28 states of European Union, and you can see clearly the downward trend of exhaust emission due to the standard, the very efficient standard for primary particles in the engine, but the wear emissions are not only increasing slightly in terms of kilometers driven, but they are also increasing relatively to the total emissions from road transport, and we expect that already in 2014 there was the point of inflection where the wear emission were higher than exhaust emission. So imagine that now probably at 2022 we are already at wear emission are very much larger than exhaust emission. Let's make a brief introduction, even if probably this is not necessary, but of the different non-exhaust emissions. First of all, the brake wear, probably the most known. Particles are coming from both the abrasion of the pad and the disc. So we call the pad and the disc the tribological couple, or the friction couple, because particles come from both product, let's say, from both materials. Normally the discs are responsible about 60% of the total brake emissions. For tire wear, there is a clear indication that they generate also particles to be airborne, but most of them are also deposited directly to the road and are of higher concern for microplastics pollution. Generally, however, for the airborne emission, for PM emission, the value of emissions are lower than brake wear. For road wear, we intend as a road wear emission the direct emission to the atmosphere from the erosion between the tread and the road surface. However, most of it most of the particles coming from road wear deposit remain in the roads and are resuspended afterwards in the process of road dust resuspension. So the differentiating the road wear from the road dust resuspension is really challenging. That's why sometimes you don't find road dust resuspension in the source apportionment studies or the other way around, because they have very similar chemical fingerprint, and we need to improve our source apportionment tools to be able to separate the two processes. In any case, the road dust resuspension is provoked by the wind, but mostly by the turbulence induced by the movement of vehicles. Some people claim that road dust resuspension may be seen as a double counting in emission inventory. But in my opinion, this is not an issue. There is no issue of double counting because there are different processes. The direct emission from the resuspension. Actually, you can see a clear, in our field observation, we can see clearly the difference that when there is humidity, high humidity on the road, you still have wear emission, but you don't have road dust resuspension. So the road dust resuspension should be included in the inventories. There are others, minor, probably non-exhaust emission, like clutch wear, where there is no almost bibliography. But I can tell you that in an ongoing project, European project called NPETS, you will find soon the first laboratory test for clutch wear emissions. There are also volatile organic compounds emission from car care products like the icers, clean wash, etc. But these are, of course, less important in terms of particle mass, and also number of studies from this is very limited. A little bit more information about the brake wear emission. As I say, there we have to distinguish between the disc, which is mainly cast iron composition, while the composition of brake pads is really variable, depending on the type of vehicle, depending on the manufacturer, and depend also if the pad is an original manufacturer product or is an aftermarket product. Each pad has a large number of ingredients due to, for example, friction modifiers. We have both lubricants and abrasives. There are also fillers, which are needed to make the whole mixture thermally stable. There are also binders like fibers, phenolic resin fibers, graphite fibers, and so on. And then there is also a reinforcing constituent, which often is made up of steel, pure metals, and also some silicates or even organic, some different polymers. In general, the brake pad composition can be differentiated in three main families, which are called now, low metallic and semi-metallic. So the content of metals increase going from now to semi-metallic, and while on the other way, the organic fraction decreases from now to semi-metallic. Mostly in the US and I guess in Canada, the now dominates the market. In Europe, instead, is the low metallic pads are dominating, while semi-metallic pads are mostly common in low-income countries. For tire wear, we know that during his lifespan, a tire loses about 1 kilogram of mass, which about 5 or 10% falls in the Pienten fraction. Again, we have a big list of ingredients which may be responsible for the particles from tire wear that are seen in the atmosphere. But the main tracers here is coming from the sulfur and the zinc we used as a vulcanizer. For road wear, it's important to say, if you look at this graph, it's important to say that the process of road wear can be normally happens everywhere, but in north countries like Canada or Scandinavian countries, if the studded tires are used, are allowed, then they generate order of magnitudes of road wear emission higher than typically no snowy countries. So this is crucial for road wear. Is crucial whether this kind of studded tires are used or not. For road dust resuspension, we observe also quite a variability of chemical composition of this mixture, very large mixture of particles. Here you can see, for example, that in the Netherlands, most of the particles resuspended are made up by wear particles, tire and brake dust. While if you move to Barcelona, the share coming from typically mineral particles, so coming from road wear or even other sources like construction activities, is the dominant one. So when we talk about road dust, we need to be careful on the sources of road dust, where this dust is coming from. About VOCs, this is an interesting study published by Roy Harrison and co-authors. It seems to be an increasing concern about this product that can provoke, as like screen wash and the eyes, that they provoke VOC emission from non-exhaust. They can come up, for example, in the UK, they calculate they come up about 7% of the total anthropogenic VOC emission, so it's significant. But the potential of ozone formation from this VOC seems to be lower than other VOC emission like evaporative loss from gasoline. Now I would like to explain very briefly which are the typical approach of studies for determining the impact of non-exhaust emission. We can separate between two families, the emission estimates and source apportionment studies. The emission estimates can be done in two different ways, like calculating one single emission factors, mostly in laboratory studies, but also in the field. While total emission inventories are based on calculation of literature review of emission factor and calculation of activity data like traffic volumes, and they are calculated for a domain, a geographical domain like European Union or national level. In red, I like to highlight the constraint of each approach. In the inverse modeling in field studies aimed to calculate emission factor, normally we have a lot of noise because, of course, there are many other sources rather than non-exhaust sources. So we need really to deploy the state-of-the-art instrumentation in order to increase the signal with respect to the noise. So this is the main constraint. For laboratory studies, the constraint is the representativeness of what you are studying, because you are the number of variables is limited. For example, you can study a few tires, a few roads surfaces. So the results are normally limited, valid only for those materials, and you cannot really extrapolate to the real world with an old fleet circulating. And for the emission inventories, the main uncertainty is due that they rely on emission factors from bibliography, so there can be a lot of uncertainty depending on which value are you taking, and also activity data can be affected by uncertainty. Then we have another family, the source apportionment family, which is divided by receptor modeling and dispersion modeling. Both of them can do source apportionment. And again, the receptor modeling approach is based on the collection of samples at ambient air level and chemical characterization, plus the application of multivariate analysis, which can allow you to differentiate the principal sources of PM, like PM10, Here, the main constraint is that often these sources contributions are related to tracers, but it's difficult to find unique tracers. So you really need to make a very comprehensive chemical characterization to be able to distinguish, for example, the vehicle non-exhaust. For dispersion modeling, using labeling tools, they have the main disadvantage is that, again, they rely on emission factors, so they can have uncertainty, very large uncertainty, and probably 100% or something like that. The importance of non-exhaust emission, however, is growing as the growing importance is a result that's coming from all these kind of inputs. So it seems to be a consolidated result from the scientific community. Here we can see that at the European level, if you look at the absolute value of emissions here on the, I hope you can see my pointer. You can see here the exhaust emission in well, PM10 and PM2.5, which are the same, which are decreasing from the last 20 years, while the wear emissions are stable or slightly increasing. And we have here the flex point where in 2014 we have the wear emissions are higher than the exhaust emission. As a percentage of traffic emission, again, we have this switch from wear to against the exhaust emission, but basically wear emission are already about, probably we are around 70% or 60% of total traffic emission in PM10. In absolute, with respect to the total number of sources, non-exhaust emission represent about 5 to 8% probably, but this is of course higher when we look at the urban domain. This percentage is of course higher because this is the total emission inventory at European level. A specific case of the European Union is Germany, where UBA calculated more or less the same trend. You can see here from the year 2000. And we have here the free, since 2018, they calculate the free contribution from brake wear, tire wear, and road abrasion, which are mostly split 1/3 each, which are again increasing. But again, road dust suspension is not included. So imagine which is the real situation when you include the emission factor from road dust resuspension. Here we have the projection until 2030. So we can see that there is no expectation of reduction of non-exhaust emission because there are no technological measure applied and no expectation of their application in the short time. For California example, this is the first emission inventory that included resuspension, clearly resuspension, and you can see clearly that the percentage are extreme because we can see here the about 70 to 90% of no, sorry, this is kilotons. If we go here to percentage of road traffic emission, 80 to 90% of PM10 is coming from non-exhaust, while exhaust is getting lower and lower until really very low significance. We have to remind that these are referring only to primary PM, so any secondary aerosol coming from the exhaust emission is not included in these plots. Coming back to the source apportionment tools, here you can see in blue the typically approach of the dispersion modeling. They first calculate the emission factor from the sources, and then they apply the physical and chemical processes and dispersion, and they calculate the exposure. So this approach has the advantage to apportion also secondary inorganic particles. But the main constraint is that they only apportion the particle mass that can be modeled. So normally, Maria Teresa is more expert than me, but mostly they have like an unmodeled part about 30%. So this is a constraint. On the other hand, the receptor modeling in green has the advantage that all the measured mass is apportioned because it starts from the measurements. But the cons is that the secondary inorganic PM is not apportioned. Here we can see an overview, a worldwide overview of source apportionment studies for non-exhaust emissions, where we compare different non-exhaust process. We compare the PM10 contribution with the PM2.5 and also with the exhaust. So we can see that the range of variability is very high, because here we are studying about, I believe it's more than 100 studies. So it's very wide variability for raw dust contribution, but we have a median about 20% of PM10 and about 8% of PM2.5 coming from raw dust resuspension. At a background level, this is important, which is similar to the exhaust contribution. It's also around this range. But we can see that while in PM10, the raw dust resuspension is higher than the exhaust, not the opposite is true for PM2.5, because the size distribution of raw dust is much coarser, so the impact in PM2.5 is much lower than the exhaust one. Concerning brake wear and tire wear, you can see that the impact in terms of mass is lower than resuspension and then exhaust as well. They are more or less similar. But brake wear in terms of PM2.5 seems to be higher than tire wear, because the size distribution of tire wear is getting more to the right hand of the distribution, so coarser particles. The same plots has been done for street level concentration, so curbside measurement site. Here we can see that more or less the scenario is the same, but raw dust could achieve really high share of PM10 until 75%. This is not really common, but probably only concern places where studded tires are used. So this is mostly due to road wear. And the brake wear increase at street level concentration. The brake wear is higher, more important than tire wear, seems, at least from this plot. Some example for country, we can see that the road dust resuspension, the highest contribution are observed in Scandinavian countries like Sweden, where it's about 74% the median, versus a very low contribution from exhaust. An average situation is coming from Central Europe, Germany, Czech Republic, and where the road dust and the exhaust are similar in terms of contributions, while in Mediterranean countries we can see an intermediate situation where, due to the more let's say dry environment, we have more resuspension, and another probably outliers coming from China, and the reason is unclear. We don't know if it's due to the level of maintenance in the roads, which is lower, or even because all the diesel vehicles are not in the cities. This is a little bit unclear, this kind of results. In terms of source contribution, the case study of Spain, these are measurements. These are not emission inventory. You can see that in across 7 years, the vehicle exhaust was reduced by 0.4 micrograms per cubic meter per year, while the road dust did not show any statistically significant decrease. But a stable pattern, so because no measure are taken against this kind of source. Regarding the health effects, Normally, these epidemiological studies are performed using exposure indicator, which can be elements or source contributions. The elements have the problem that they are not unique tracer. For example, copper is very commonly used, but copper is not only coming from from breakware. Some metallurgy processes can also emit copper and others. So we have to take with caution this kind of studies, while source contribution indicators are probably more reliable. In any case, this is the summary, the review done by OECD at the global level for mortality and morbidity. They found that all these elements related to non-exhaust emissions showed a statistically significant mortality on the short and long term, which are more relevant, the long term, of course. But also for mortality, both again, it's like total PM. They affect mostly the cardiovascular and respiratory illnesses, but there are also some specific studies on other symptoms or biomarker like lung function, low newborn sizes, blood pressure, preeclampsia, etc. So it seems to affect mostly all the human body without a specific pattern like other sources. You can see here also diabetes, also the metabolic system is affected, also the reproductive and also the high blood pressure studies have shown significant result. Another proxy used for effect is, as you know, oxidative potential. This is a very interesting paper published recently by PSI in Switzerland, where they apportion the oxidative potential due to reactive oxygen species generated by different type of particles. And for they found out that while the mass of particles in the ambient air is very complex, coming from different source, the indicators of oxidative potential like DTT or ascorbic acid are mostly related to vehicle wear and secondary organic aerosol. So in these maps, you can see that while the concentration of particles is really due to different sources, but mostly the mass is dominated by secondary inorganic aerosols and crustal material. If we look at the map at the sources of DTT, so oxidative potential, most of the oxidative potential across Europe is due to vehicular wear in the cities and also in the regions very highly densely populated, like Netherlands, Belgium, and UK, from vehicle wear. So now, if there are no immediate questions, I would like to analyze a little bit in detail which factors are influencing the burden, the magnitude of non-exhaust emission. Here I took this list from the report from OECD, where they analyze in a qualitative way the impact of each of vehicle future, road futures, driving, so the driver characteristic and the weather characteristic, how they could affect the single non-exhaust processes. And we will analyze in the next slides the most important one. For vehicle future, it seems that most of the most important are the weight of the vehicles, which affect mostly the emission potential of direct wear emission, the rotor temperature, so the temperature achieved by the friction couple in the brake seems very important, mostly for the ultrafine particle generation. The studded tires, as I mentioned earlier, while there are only few studies which try to relate the tire diameter and width with the emission potential, and seems to have the higher diameter, the higher the width, the lower the emission potential. But there are only few studies. About the road features, the maximum speed, the higher the maximum speed allowed, the higher the emission potential for all the sources, non-exhaust sources. Also, the weight allowed in each street can influence directly the emission potential. The state of the pavement, as I mentioned earlier, and the road dust loading. The amount of dust per square meter deposited on the road is directly affecting the emission potential, like the old EPA AP42 model. Instead, the road moisture, the higher the moisture, the lower the road dust resuspension. For driving features, of course, the speed is a crucial point. There is a quadratic relationship between the speed and the emission from resuspension. Acceleration and deceleration, this is an increasing topic of research. Given that electric vehicles have a higher acceleration than internal combustion vehicles. Aggressive driving, of course, this is related to rotor temperature, and all increase the emission. Concerning weather condition, the temperature increase, also the wind speed increase the emissions, while precipitation works in the other way. A little bit more on speed. We published here in Milan that the change from 36 km per hour to 57 per hour in the same street was increasing significantly the emission factor from resuspension by a power relationship of 1.5. So these are experimental data, and here this is a modeling study in Sweden, where they see again that the speed is related to an increase, the acceleration, so is related both in a positive and a negative way. So acceleration and deceleration are related to the higher emission factors. Going to road dust loading, well, I think I can skip this because I see that we are already right? We already passed half an hour. This is important because the road moisture has been proven already from the 90s to be very related to the emission potential from resuspension. And we have here estimated that from a rain event here at time 0, this is the rain event, there is an exponential recovery of road dust emissions of really few hours. This is the case, I think, of Barcelona, with 24 hours reaching 90% of the emissions. So if we have a precipitation event, this will affect only during one day on average the reduction of emission, while, for example, for the Netherlands is about 3 days. Vehicle weight, this is extremely important because the scenario of vehicle market in Europe, but probably all over the world, are showing an increase of sport utility vehicles, so very, very large cars. In Canada, I guess, is even more important. And so there is, if you look at all passenger cars, average mass in the market is getting larger and larger within the last 20 years. This has a direct impact on the emission from brake wear, road wear, and tire wear, at least. And from the Argonne National Laboratory study in France, they estimate that the increase of mass from large electric vehicles with 300 mileage range is about 30 to 40%. How this is translated to higher emission? In the study from Meadows and Harrison in UK, they show that increasing the tons of the weight of the vehicles has a direct impact on the emission potential from tire wear, brake wear, and road wear. So the three of them, all the three sources are increased. But also resuspension, although they calculated this using the AP42 model, which has large uncertainties for the European case. let's go a little bit more inside the issue of electrification. Of course, we have positive aspect. This is cannot be denied. There is no exhaust, no evaporative emission. We have regenerative braking, which is very efficient to reduce braking emissions. But on the other hand, we have an increased weight due to the battery pack, which can achieve even 30 to 40% of the internal combustion counterpart. Potentially, there is also a different driving style, because not due to the driver, but to the way of to the power of the engine, which is provoke higher acceleration in the electric vehicle. So we need to keep in mind that generally for exhaust emissions, the electrification is good. There is no doubt on that. But for non-exhaust particles, it need to be investigated in depth. There are already several indications, like the report from OECD, where they estimated that for passenger cars, the PM2.5 and the PM10 from electric vehicles were lower than the internal combustion counterpart, but only by 12 to 18%. So a really marginal reduction of non-exhaust emission due to electrification, but surprisingly, when we increase the dimension of the battery pack, so the mileage of the electric vehicles, this can provoke even an increase of non-exhaust emissions. Another similar result is coming from the CARB study in California, where the Toyota Prius was tested against other vehicles, and they see that only for brake emissions there is a significant reduction, because again, as we said before, the regenerative braking is very efficient to reduce brake emissions. So here we're talking only about brake emissions. Instead, when we look again at the overall non-exhaust emission factor as a sum of all the non-exhaust processes, Beddoes and Harrison found that again the reduction is about 20% of with respect to internal combustion engine, and not in all cases, because depending on the type of electric vehicles, this can be even smaller. Here we can see that an overview of total emissions, including also secondary particles. Why do I show this? Because here we can see the total effect of a comparison, comparing one new car, Euro 6 new car, diesel and gasoline, with a new electric car. For passenger car, there seems to be a marginal improvement in terms of total emissions due to mostly to the regenerative braking. The tire wear emission, which is this dark purple, is slightly increased due to the increased weight for the battery pack, but this is not enough to provoke a higher emission in the electric vehicles. So the regenerative braking compensates this increase due to tire wear. These are, of course, all estimates based on the bibliography studies, theoretical assumption, but it's quite robust in terms of, because it's based on a worldwide literature review. But when we move to sport utility wagon, we see that this reduction is even smaller. So the larger the mass of the vehicle, the smaller the difference between the electric and internal combustion vehicles. And for light commercial vehicles, the scenario is similar to large cars. Of course, this comparison needs to be improved, because there are quite few studies, experimental studies so far. So which are the main challenges in the research in this field? Resuspension, resuspension that here is calculated as this lighter purple is very is an estimate is estimated not to change from internal combustion vehicle to electric, while it could change, and also depends very largely on the site where you are measuring. So in one site could give different results from another. The relationship between weight and emission factor can be improved with a higher number of studies. The acceleration rate is not considered. As well, the undercarriage, the flatter undercarriage of electric vehicles should be considered, because it provokes less turbulence. And the secondary oswald formation, so this part, the gray part, of course, is quite uncertain, and also could be improved, because of course the processes of formation are not linear from the emission of precursors. In this direction, we have developed a project here at a Spanish level. This is a Spanish project, but with the contribution of several international companies and these institutions, aimed at demonstrating on a field, on a proving ground, the role of electrification in terms of non-exhaust emission measured both on board and at a roadside. What we compared was the 3 different vehicles of the same size, but different mass. We can see the internal combustion vehicle, which with a total mass of 2100 kilograms, the plug-in hybrid 2500s, and the fully electric vehicle 2700s. These 3 vehicles were running through this circuit in 2 different kind of test cycle. These are, you can see here, the speed that were reached, which were the same for the 3 vehicles. And we analyzed both the particle mass and the particle number emission. Here on the right, we can see that the map of particle mass measured in real time with 1 second resolution. And we can see that the higher values were observed for the electric vehicles due to probably the higher weight. And interestingly, there is also a change in the moment where these particles were emitted. While the internal combustion vehicle and the plug-in were polluting more during the braking and the acceleration, during the braking activity rather than the acceleration. You see this peak is larger than this. The hybrid shows a quite similar scenario between the 2 peaks, while the electric vehicles show a much higher peak during the acceleration rather than the braking. These are very preliminary results. I must say that you are the first people looking at the results, because we produced them last week. So we really need to go in detail, because we have like hundreds of cycles. So we really need to make more statistically robust analysis. But there is an indication that the acceleration in the electric vehicles is a reason of higher resuspension emission due to the electric vehicles, while the braking, which heavily affected by the regenerative braking, is much lower. So the friction braking is much reduced when compared to the internal combustion vehicle or the hybrid version. When we look at the particle number emission, we see again that the higher emission are coming from the electric vehicles, but while in the mass, the ratio between the electric vehicles and internal combustion was about a factor of 2, so twice, a factor of 2 higher for the electric vehicles. For the particle number, this ratio is much lower. So the emissions are quite similar, but slightly higher for the electric vehicles. And the reason of this is more difficult to understand. We see again that there is a change in the moment where the particle number emissions are occurring, while the internal combustion vehicle was emitting during the cornering. So during the slowdown of the vehicle in order to start the cornering, and also for the hybrid version, the highest peak for the electric vehicles in particle number were coming during the braking event. So probably the little friction braking of the electric vehicles was high enough in terms of particle number to compensate the reduction due to regenerative braking. So the peaks are similar, but are due to different processes. So what is the projection, given these preliminary results? What are the projections made by OECD in terms of future scenario with the electrification of the fleet? There are two different scenarios, the 4% uptake and the quite aggressive 8% uptake of electric vehicles at the global level. And none of them achieved to reduce emissions, non-exhaust emission by 2030. Mostly for PM10, but also for PM2.5. So we have an issue with electric vehicles. Non-exhaust emission reduction are marginal or even higher, both in terms of mass and numbers. So that we have to also cope in the future with this aspect. I will skip this because just not to repeat, and I will move now to policies which can affect both the vehicle technology, first by establish measurement protocols and emission standards, like the work we are doing in the European Union, but also promoting a broader use of regenerative braking, and also regulating the material composition for tires and friction materials. Lightweighting should be encouraged in the market, given to the high importance of the vehicle weight. At a market-based instrument, mostly the adoption of small and lighter vehicles should be also promoted by taxes, ownership and registration taxes. So not only the power of the engine should be a criterion for these taxes, but also the size and the weight. And also should be promoted the adoption of less polluting vehicles in terms of non-exhaust processes, using, for example, filters which are not yet in the market, and disc coatings. At the traffic and road management policies, we need to increase to decrease the speed limits to the weight of the vehicle that can access the roads, mostly in the urban centers, and improving the road washing due to the clear effect of road moisture and the studded tires as well. Road pricing can also be a measure which should be based on the distance that has been traveled. At the European level, we are really taking advantage of the work done by the UNECE, where a working group was working on has been working the last probably 6 years, trying to identify a common protocol to measure and brake emissions. The results has been published in 2018 from Matisse and co-authors, providing a common procedure common test cycle, which is called WLTP brake test cycle, to measure a real world, something really close to a real world test cycle for a bench dynamometer test. So this cycle lasts about 4 hours, reach a maximum speed of 130 kilometers per hour. and it's been used for the Euro standard, will be used for the new Euro standard, Euro 7 standard, which is coming to force from 2025. This standard is the first one in the world to limit the emission from brake particles from passenger cars and light commercial vehicles to 7 milligrams per kilometer. And it's the type approval details, the type approval test details will be available very soon with a GTR regulation, but I can give you some details. For example, the WLTP brake test will be applied, as I mentioned before, and to these 7 milligrams, a reduction will be applied to electric vehicles, about 85%, and somewhere in between for hybrid vehicles. This and how this 7 milligrams refers to, with respect to the current numbers observed in literature. Here we need to stop and make a little bit of differentiation between what is measured in the real world, like in our proving ground test in Spain, and what is measured in the lab, where this WLTP brake test cycle is tested. If we were in the real world, 7 milligrams would be quite conservative. Normally we observe this kind of values in our field observation. But when we measure with WLTP, the numbers are much higher than this. So in my opinion, this is a very challenging target to achieve. And the automotive industry must really make a huge effort to achieve this standard for the type approval test. This morning I was talking, for example, to Audi, and they say that they are really putting a great effort in the coatings of the disc in order to achieve this value for the low price car. But for exclusive cars, they are already thinking about installing the filters in the wheels in order to achieve such, which is much higher, of course, a higher cost. For example, when we look at bibliography studies in bench dynamometer, in brake dynamometer, we see that here, for example, in Garg et al., this is quite old study, but they already achieved 12 milligrams, and the maximum speed here was 50 kilometers per hour. So imagine if we go up to 130 kilometers per hour and higher deceleration, how this value will rise. So 7 milligrams is really low. We can also see more recent studies from Magino-san, and we can see that they reach 1 milligram per vehicles, but again, the speed was only much lower, and I guess also the deceleration, yes, is much lower. And Perricone here in Italy, in Italy, found up to 47 milligram per stop, which means that imagine how much it would be for the whole cycle. So it is really a challenging value, and we will see how the automotive industry will respond to such value. So which option do they have? They have mostly the regenerative braking, which will help very significantly for hybrid and electric vehicles, but for the internal combustion vehicles, the options are to modify the friction materials, but mostly the coating the brake disc, which seems to be the most cost-efficient measure to be applied. And also some is considering to reuse the reinvent the wheels, or reuse the drum brakes in order to contain the particles within this enclosed box. And again, for exclusive car, the use of filters inside the wheels. For tyre emissions, the European Commission is also working hardly. They commission they asked IDIADA, which is a Spanish institution, to develop the standardized method, and this will be for the abrasion test, and this will be available soon, but probably we need to wait 2025 to have the official standard, and so on and so for the limit value. I would recommend, if you're interested in ongoing projects on non-exhaust emission from the European side, and to look at these 4 projects which are actually ongoing. The next is our project at Spanish level. The Leon-T is a recent project started last year, where they are developing low noise and low particle emission tires. The NPETS project is, I mentioned here, just because they look at non-exhaust emission, ultrafine particle emission. So this is very innovative, and also the first clutch wear lab has been developed. So interesting result. We will see how much emission we come from the clutch. And the Vera project is the most recent one, will try to optimize the retrofit solution for already existing vehicles, both for tailpipe and brake emission. I recommend, there are many more, but these 3 documents to be studied for doctoral students. I think they are quite comprehensive in terms of mitigation policies, and also emission factor estimation methods, and also epidemiological studies, and nothing more. I would like to thank all of you for your attention, but also all the people that helped me in with sometimes even confidential information to draft this presentation. Thank you very much.
Thank you very much, Fulvio. It was a brilliant state-of-the-art of non-exhaust emission. We are running out of time, so I don't know if I already shared your email in case someone wants to address you directly by email for a question or comments or whatever. Greg, do you think we have time for any question, or?
If you have time, I think those who have to move on to another meeting can, but I certainly like to see if there's any questions. I had a number of questions, but you answered them all as you went through your talk, so congratulations.
I'm sorry, it was too long. Sorry.
No, it was wonderful, and thank you for sharing those. There's new results, so there's lots of intriguing things, but I'll let others start, and if not, I had a couple of questions. So does anyone, you can either put it in the chat or use your microphone. Let's see if there is, I don't see anything in the chat yet. I put a question in the chat, so Lauren had one. Lauren, do you want to re-ask your question?
Yeah, I can just quickly say it if that's easier. So thanks for your presentation. I just had a quick question. This maybe it's just like a small aspect of your presentation, but I know you didn't touch on this. I've heard that some countries have begun recycling plastics to create new roads. And I was just wondering if you have any thoughts on this, like if I know it's an initiative that would like repurpose plastic waste, but I'm wondering if down the road this could just increase plastic emissions from road wear. So I'm not sure if you're familiar with that, or if you have any thoughts on that, but.
No, not really. It is too recent to have some experimental evidence. So I will not. I don't feel comfortable to comment on something that I didn't really study.
Great. Well, thank you for the question, Lauren. Anyway.
Thank you.
I'll ask one. So I was very interested in the mitigation methods you suggested. You've suggested road washing or road sweeping, which is something that's quite interesting to us. But in terms of the road washing, you showed us some results saying there was sort of a 1 to 3 day recovery time after a heavy rainfall, I think it is. So I'm wondering if you could just tell us a little more about where or how those results were developed, and whether road washing can be effective if, if we do it once a week, then we'll have emissions for 6 out of the 7 days if there's a 1-day recovery. So, how much can we hope to gain from that sort of strategy?
Okay, this must. The first thing is that the results come from quite dry environment in Spain, and it's not really applicable to your environment. But in the Netherlands, we saw that the effect was even lasting longer because the evaporation was lower than in Spain. But we have the problem of below 0 degrees higher temperature. So we need to be careful before advising in very cold climates to apply cold washing, to apply road washing. Again, there is no much studied in very cold countries. So what I can say is that in Spain, for example, we advised and the local authorities, and this was applied from the city hall to increase the road washing frequency when Saharan dust outbreaks are expected. We have this dust coming from Sahara, which increase dramatically the PM10 concentration, also the road dust loading. Yeah. So we have a forecast, an established forecast of this. So they know that when they receive the alert of the Saharan dust, they increase the frequency of road washing. So for air pollution episodes in Spain, it is a valid measure. Of course, it reduces not much, about 8% of the concentration, but can be one additional measure to mitigate.
Yeah, I think so. There's some hesitation about road washing here, just because the runoff goes into the rivers, and we're already concerned about the microplastics. So we have been looking at street sweeping, and they're even using newer, higher tech street sweeping. We don't see as much difference as we would hope to. And it may be because the recovery time is pretty quick, that most of the removal is actually occurring through vehicle resuspension, that the washing and the sweep-in is actually small overall compared to how much has been removed by the vehicle resuspension, in which case we're kind of stuck. It's going to get on the road, and it's going to end up in the air.
Exactly. Actually, in one review in 2010, we saw that no studies were really demonstrating that road sweeping only without any moistening was able to remove the particle, the finest particle from the road. Like they're embedded in the porosity of the asphalt. So only the moistening was able to increase their mass and make them stick on the road for a while, but the sweeping was not really showing significant results.
Yeah. I'll leave it to see if there's anyone others who have questions. Anything more in the chat?
Try to read it.
Jade, there's a question here from Jade. I see it in Taylor. Why don't you read them and see if you can answer?
I have one question about the Euro 7 sign. Notice is a new standard the EU is restricting the PM emission from building. Like the limitations for abrasion. Same to the test procedure of these two sources. Okay, the difference between brake wear and tire abrasion is due to the fact that the microplastics are also involved. The Commission is very interested also in the generation of microplastics, which are normally higher in size than PM10. So they first want to use a overall tire abrasion test in order to consider both of them. And later probably they will go for a pure tire wear, so air quality related protocol, if I understood well the question.
Yeah, I think so. I had a follow-up question on that. So We have, I would say, much too little, if not almost no control on what's used in brake pads in Canada. They seem to come in from all over the place, and it changes all the time, and people don't pay much attention to it yet. I gather the hope is that there'll be a lot more attention paid to it in vehicle manufacture, and also when people switch their brake pads, because as we all know, our brake pads don't last forever. We need to switch them all the time. So I'm wondering if you've seen anything on that, for example, coating the discs will help for a bit. But the brake pads themselves, it really seems wide open as to what gets put into a brake pad and where it comes from.
Well, for Canada, there's is quite limited bibliography. I cannot recall much, but my understanding is that the market should be the same as the US. This is my understanding, right? So I expect that you use NAO, so non-asbestos organic pads. So normally these pads show quite low brake emission in terms of mass, lower than the European region, but a higher particle number concentration. So I expect that particle number from brake wear should be higher than in Europe, but it is difficult to say that it will become a significant source of particle number in ambient air, because we are still very, very below, order of magnitudes below the exhaust particle number emissions. Regarding other type of regulation, I'm not sure if Canada has any regulation about asbestos.
We do finally.
You do finally, but it came late, right?
It did come late,
Okay.
and so there's probably still brake pads out there that have asbestos or road dust out there. Yeah.
So if I was in Canada, I would not regret to study asbestos in the curbside. I don't know.
Yes. Yeah. All right. We're 10 minutes after the hour, so yeah. Thank you very much for a fascinating presentation and all the incredible work you're doing. And we'll be more than happy to keep you posted on our progress here.
Okay.
Thank you.
Thank you
Thank
so
you,
much.
Fulvio.
Thank you.
Thank you very
Have
much.
a nice
evening.
day.
Yeah.
You too. Bye-bye.
Bye. Bye, everyone.
And thank you all for joining us. Yes. Thanks, Maria.